So hello everyone. Today I'm going to share some new idea from my first year PhD paper, which is the Composable and environment-aware federated learning models. This work is done with my first supervisor, Dr. Lito Michala, and Professor Trinder. Okay, I hope that this will be an interesting topic to talk, and I hope that you can be interested in this direction. So first, I want to talk about share some backgrounds on what is federated learning and how it generates a machine learning model, and then I'll share the reasons that motivated me to do this with Elixir, and why using Elixir could be a straightforward and flexible and versatile way to do this in a distributed environment. And then we have a look at the implementation using Elixir. Then we talk about the experiment results, and finally we come to some conclusions. Okay, so first thing first, what is federated learning? To do the federated learning, we first will have a private server, which is probably sitting on some cloud provider, and then you have a number of users that is distributed all over the world. Then this private server will randomly select a subset of users, and those users will submit their local model to the private server, and then this private server will output a global model that is a combination of those individual models, and this global model is expected to perform better than those individual models, because we see there, if a user see maybe like 100 samples, and then you have 5 users, and you have maybe around 500 samples. So this global model, could perform better in this scenario. And then for the second iteration, we will first sync the global model from iteration 1 to all the users, and then we repeat this process. We select another subset of users, and then we gather all the individual models from those users, and we have another global model. Then, you can do this until forever. So, this went well until the fall apart. Sometimes one size for all is good, but for some scenario, it doesn't work well, and for some use case, we really want the model to perform, to have the accuracy in that scenario. So how should we deal with that problem? In this paper from Google and MIT, they point out that so data at source are typically far from IID. So this is kind of the problem that creates this this corner case for us. And for some users, maybe they use the devices less frequently. So the device has less observed samples in on that device. And sorry. Another problem is that the quantities of the data are typically available at each device is different. So we have this imbalance problem, which causes a further problem for the global model to deal with different and to perform better in the complex environment. So, for example, let's say that for some use cases, we can see that we maybe naturally have this group. Maybe you have 3 users in environment A, and you have another 3 users in environment B. And so the idea is that if we could gather all the users that in the same environment and we create a specialized model for those groups, then it could potentially perform better than a one-size-for-all global model. And another example is that, in this paper, they point out that, for on the East Coast, maybe you have a set of plants you can observe, and on the West Coast, you have a different set of plants. So this visually difference is naturally in our real life, in the real world. So I think that if we can be one step closer to the real world data distribution and solve that problem with Elixir, that could be a direction for better performance. And sometimes the former case, we have all three users in those environments. That's basically like the ideal situation, which never happens in the real life. So more likely you will have this imbalanced distribution of users. Maybe some environments, they have many more users in that environment. And for some environment, you only have just a few users in that case. And another problem is that these users, they can move freely from one location to another location. For example, a autonomous car can drive from East Coast to the West Coast, and the geolocation changes will cause the data distribution to change. And potentially, we would want to use a specialized model when we drive from one location to another location. How many possible environments we could have? Well, there's quite a lot on Earth, and so let's see a real example. Like, for example, for an autonomous car, you can drive in desert, in city, or you can drive on mountain, and you have different weather conditions like rain, fog, or snow. Or we have this thunderstorm right now in here, and we perhaps would want to use a specialized model for to deal with this situation. And more complex example is that sometimes you don't have one simple environment. Maybe you have a composite environment that is a combination of two or more basic environments. For example, you may have this rain and fog situation. Sometimes you have this snow and fog situations. So for my model, I kind of like imagine that if we take the digit 4 as example, then we would expect this to be the normal situation. Sometimes we have this in the simple environment, and maybe have a list of simple environment, and sometimes they can form this combined composite environment that is maybe 2, or the real complex example that is a combination of all the 3 basic environments. And an intuitive explanation that why a global model could have some problems in some scenarios. For example, we can see that let's say that this blue line is the data distribution for the normal environment, and we have this rain and fog and snow data distributions. And the Federated Learning global model will try to approximate this purple dotted line here, and this purple dotted line, well, it works in various environments. However, for this case, when you only have this rain and fog situation, and when you apply this Federated Learning global model, then, well, it may not follow the real data distribution, which is the green dashed line here, and for this fog and snow example, we can see that this federated learning global model it works, but well, for some cases it might have some drawbacks, and that's where I want to address the problem, and I want to solve this problem with Elixir and so we can see that let's see a example here, like we have two agents, agent 1 and agent 2, and this is the place that they could go, and agent 1 could take this path from this environment to the rainy environment and goes to here, and the agent 2 could follow this path, and those two agents they can observe different samples in different environments, and my solution or my idea is to when this agent follows this path, and we can try to do this environment aware partition for all the data it observes from all the sensors. And for example, for the snow environment, while it follows this path, we can when we observe one data point, we can and with the environment tag, we can connect it to this blue square here, and then we can and when the H1 goes to enters the this area for this intersection area, that can depend on your configuration. It is possible to have of course a composite text that is a combination of this snow and rain, and after that we can, when we gather all the data from snow environment and the rain environment and the other environment, we can actually this is a online machine learning. We do this on the fly, and we will first train local models using this data, and this model here is the local model for the snow environment. This blue square is the local model for this environment, and then we do the same thing for agent 2. After that, we upload those tag model updates. The tag is the environment tag, and I will explain that how do we obtain those tags with Elixir, and how and the performance of this model. And after that, we upload this to a central or a central private server, which depends on your configuration. After that, you can this private server will gather all the models from agent 1, agent 2, and so on, and we can have this, and then we can now do we can combine this to a specialized model. So this is from the model from agent 1, and this is the model from agent 2, and this private server can combine these two models or maybe more in the snow environment to form a specialized model, and this model will be used for this environment. Well, sometimes maybe this agent 2, you see, it only follow it only stay in this area for a short time. So maybe the data points or the model it produced is not quite good. So we need to. So I borrowed the idea from genetic algorithms, which is the innate selection process to select the model that has a that performs has a good performance. For example, this innate selection has a parameter R, which you can set that R to 10%, which is to take the top 10% of all the models in the Renyi area to form this specialized model. And then after you have all the specialized model, you can further combine them to form this new composite model. For example, this WE1 and WE3 can form a composite model for the snow and the fog environment. And the conventional federated learning approach is basically they will just select all the updates and they generate the global model. So this is basically when you have more information from the environment, then you can do this process to select and combine the models. Whereas the conventional approach, they simply just take everything and mix them together and output a one-size-for-all model. And how do we obtain this environment text? Of course, we use sensors to observe the environment. So, for example, this the implementation is in Elixir, and this is an early approach. So of course, I'm still trying to improve this library, and also we have some other dependencies. For example, like the which I will mention later. So for this sensor behavior, I want to make it really simple and to implement for any users. It only has so initialize, and then you give me one sample from the data from the sensor, and then for example, in the experiment I conducted in this paper, we basically fetch the data from using this SCI data with a MNIST dataset, and then we transform this to with the numerical Elixir library, and then we take one data from this sensor. So of course, this right now I'm using this Torch backend, and I'm developing another library named Evasion, which is a computer vision library that I will use that for my final year PhD project, and so this is like the progress by so far, and I really want to push it further. So if you ask me, is this production level? No, it's still in an early stage, and I'm also contributing to the NERVS project so that you can have some libraries for the most frequently seen sensors like the accelerator and some other sensors. So this is the progress so far, and I want to make this more easier to use when I approach my final year. But this is basically the workflow. You initialize the sensor and you read one data, and then you can. So this is the environment sensor, which actually we have two types of sensors. One is the camera, which sometimes you can imagine that is a autonomous vehicle, and then you have this camera, or you can gather data from a LiDAR sensor, and then you can have this other environment sensor that can do this environment text for you. And how do we get those tags? Here's the environment behavior, and we have this get text, which will return current text that the agent is observed, and this is the callback that you pass a list of. You return a list of sensors that is available on your agent, and then you can call it transform function to actually transform all the readings from your environment sensor to the environment tag that will be used for the models. And that text could be semantic or numerical text. So, for example, here we have this perception perception sensor, and which we say that the perception is above 10 millimeters, then we say it's reading. And if the visibility is below, let's say 15 meters, then we say that it's in fog situation. And this code here, what I really want to do is that make this really a declarative way to for the the robotic community and for them to write all the declarative statements here, and then when you have this text, you can select the models based on those tags without any if-else statement, because we actually have this pattern matching feature in Elixir and Erlang. Also, another advantage in using Elixir is that you could do hard code swapping in Elixir and Erlang, of course, and in most frequently used libraries or robotic community is Python or C++, which you well, I think as far as I know, it would be really hard to do that if you are using Python or C++. If you want to have this hard code swapping feature and the pattern matching feature, and of course this should be from my personal view, and I think this should be more straightforward to understand the visibility. If the visibility is below 15 meters, then it's fog. Then it's really easy to see what you are trying to tag your data. And for the agent, we have some callbacks, and for example, should you update your local model, and so this is based on your performance of your device. For example, the Raspberry Pi, it has limited performance, so you don't want to really do that every maybe every 5 minutes. So maybe you want to do that a little bit longer, or you want to collect 1,000 samples, then you do this update local model thing, and then you can do this and you can get the initial model from the parameter server, and another advantage for this approach is that for traditional federated learning approach, if you are using model 1 as your base model, as your initial model, and then you have to submit the updated model based on that model, and the server has and the server should also be at model 1. If the server is already at the second iteration or the second epoch, then all the data that you learned on this agent will be thrown away, or well, there are some migrations in federated learning community to deal with that, but it has some drawbacks. If you want to do that, there's no freedom. You have to do some computational intensive task to make that possible. And in my approach, so basically, if we upload this text model updates, and I choose a way that you don't really depend on the first model that the server is synced to you. So in the traditional one, you have to do this synchronized process so that you can move on to the next generation. And of course, the last thing will be the parameter server, which is also straightforward. So it will just handle the simplest one will handle 3 calls: the model update, and get specialized model, and get composite model. And this text will be passed from the agent in the request. And this text can will be used to match the models in the database or somewhere you store the model. And then for the composite model, if there is existing one that is already generated before, now of course, and it's not expired, we can just return that to the agent. If the composite model is not available at the moment, then we will, based on the text, to generate the composite model for the agent. And of course, for different texts, you can have multiple core to match this text here. And this text could be a map of fork2 and rainy 2, maybe. Or you can have some numerical text like visibility, temperature, or humidity, or maybe like your geolocation, if that is allowed in your application. So this thing here is where you can have all the flexibility to make this really convenient and straightforward, and it's easy. Well, at least I would think that this could be easy to maintain, and if there is no match in, then it can naturally fall back to the global model. So I think this could be a better way to deal with some complex environment, and it can, and in some scenarios, if you didn't cover that in your statements, then it can just fall back to the global model. And let's see some experimental results. So here, this blue welding plots the local model, which is the model we train on the agent without any communication with the parameter server. So we can see that the accuracy is not good, and then after we generate the specialized model, it performs better than the local model, which is what we expected. And for the Federated Learning approach, so the algorithm here we are using is the federated average, and of course there are some other algorithms that is has some improvements to the federated average, but I will use this as the baseline. So as we can see here, the specialized model in those 4 environments has a tendency to perform better than the conventional models, and some reaches 80% of accuracy, and this distribution is more close to the high end. And of course, some models are not as good as this one, but for this environment, the kind of the worst accuracy is kind of above this one for the traditional federated learning. And for the composite environment, for the complex environment, this is the local model for environment B, which is let's say that is some environment, and this is for another environment. And we have this composite model for the complex environment, and this is the conventional federated learning model. And the R here is the parameter that I mentioned for the elect selection process. When you set R to 10%, then you are choosing the top 10% of the models that to form your composite model. And when this parameter gets larger and larger, then the local model, although the local model is not quite good as this one, but the composite model didn't show a larger negative impact on this one. So this is the basic model for environment D, and this is the local model for environment B, and this is the combined model from using this one and this one. And we can see that although we are setting this R parameter to 35%, and in most cases, it still performs better than what we have in traditional federated learning. And we see the same trend for another complex environment. And this one we have like the kind of the best result. We have good performance on both basic models, and the composite model is sometimes the worst performance of this composite model is better than the base case in the baseline model for the conventional approach. And for some conclusions here, so since we have this real world data distribution that is non-IID because of your geolocation, maybe your customers, and some other factors. So we kind of need more information about the environment, and if we could have that information, we can tag the collected data on those agents, and then with that tag we can do this pattern matching in Elixir, and this will be a natural way to transform from those raw data from the sensors and to the environment tags, and those environment tags will naturally to generate the specialized model on the parameter server, and they can combine and generate a composite model. And another reason for using Elixir is that we can do this how they call the swamping. So if you want to add another sensor to your agent or remove sensor from your agent, you can do that on the fly, or you can define some other environments on the fly without any interruptions. And some future researches, of course, as I mentioned, I want to do this, have a better integration with frequently used sensors and automatically detect those sensors. So kind of create an out-of-box experience with the NERVS project, or maybe some other would use roles, the robotic OS. So that is also possible. So so this is one thing that I will do in the future. And of course, I want to run experiments on larger and realistic datasets, like iNaturalist geolocation and the other one. And lastly, I would like to explore with more neural networks from like ReasoNet, VTG, and Inception, so on and so forth. And lastly, I kind of so my personal interest is mostly on the machine learning part, and in the last year, I actually started to write code in Elixir and Erlang, and I saw many progress in this machine learning community with Elixir and Erlang. So I really want to. So I'm really happy to see that Erlang and Elixir can do this more computational intensive task, and it can so like years ago, this was kind of so some would say Erlang was not designed for this intensive task, but now it is possible to do this, and so I'm here to share my idea with you on this machine learning aspect, and I know that this is still in an early stage, so I will of course to improve this library further in my PhD. Thank you for listening, and any questions?
Thank you.